All right. We would like to continue looking at ANSYS Workbench. So far, you have used it for axially loaded members. And remember the element we used when we used the line concept was a beam element. A beam element is capable to capture the behavior of axially loaded members loaded in bending as well as in torsion. So far the application was on axially loaded parts. Today we want to take it to solve the problem of a simple supported beam with a load applied at its center. It's made out of structured steel, which is the default material. It is simply supported. We have a pin support at the left end and a roller support at the right end. We would like to learn about the different type of supports, how to make sure to create a model that is fully constrained so it does not fail. So we want to understand about degrees of freedom and what these supports are doing for beam elements. And we want to, again, look at creating results as in force reactions, stresses in the beam, shear and moment diagrams, displacements. So we want to be able to look at these again. Okay. So we expect that when we put the 1000 Newton at the center of the beam, that the beam is going to deform as shown. And we want to make sure when we run it in ANSYS, we get the behavior we expect. We will get the behavior we expect. So the first part is to create the geometry or the model. So I would start in a new project in ANSYS Workbench. So we start from scratch. Just saving my previous work here. But once I start a new project, I am gonna go to define a static structure analysis. So I double click. The first item, engineering data, we do not have to do anything because we're gonna use the default structure steel. Second step is to go to the geometry and I'm gonna right click to launch design modeler. So I'm gonna say new design modeler geometry. And this launched design modeler. Let me make my background white so you can see it better. From the tools. You don't have to do it. I'm doing it so you can see it, but if you prefer, I'll show you where to do it. If you go to the tools, options, appearance, under options, you get to choose your background style, background color, and so on. So I changed my background color to white. Okay. So now when I go to my design modeler, you can see it better. Okay.
Before I could see the line.
Yeah. All right. So now we are looking at this simply supported beam with support at the left side, support at the right side, and a load at the center. Of course, I can create the beam using 2 points, but then I'm not going to have a point at the center to apply the load. So I have to work with the end in mind. I'm not just creating a CAD model, but I'm creating a CAD model for simulation. So I have to create entities that I don't need for my geometry, but I need for my loads or constraints. So with that being said, we know that we are going to create 3 points and 2 line concepts. This beam is prismatic. This beam is prismatic. So even though I have 2 line bodies, they get the same section. So I don't have to create 2 line bodies. I can make it 1 line body by just adding material instead of add frozen. When you solved your homework problem, you had to use add frozen. But for this example, I can simply use add material, as we're going to see. Okay. It is very important to pay attention to the alignment because we have a rectangular section, right? We have a rectangular section. So it will be important, as you can see, to make sure that the beam is loaded along its strong axis, not the weak axis. So let's get started here. We're going to work in the XY plane. I'm going to show my planes, and we're going to use the metric units. I don't have to change my units. I simply have to create a point at x equals 0, x equals 5, and x equals 10. So I go to create point, and I'm going to change the definition to manual input. 3 zeros and generate. Here comes my first point. For my second point, I'm going to go create point. Definition also change to manual input. My x ordinate is 5 for the center point. F5 to generate my point. Third point, manual input also, and my x ordinate is 10, F5 to generate. Here comes my third point. So now I have my 3 points. Next, I'm going to go to concept, line from points, select my first point, use the control button to select my second point, apply, and this is going to be my first line, generate. Here comes my line body and my part, and I use add material. Another line concept from points, and that would be from node 2, or from the second point to the third point, apply, and generate. And I used add material, so I ended up with 1 line body that does not have a section assigned to it yet, because we have not created a section. So if I come here, I don't really have any sections. So we're going to go to the concepts to define our rectangular cross section. So I went to concepts and I picked cross section and I chose rectangular. So now I have a rectangular section that we need to define. The default here is going to 1 centimeter by 1 centimeter, like a square. So the base is fine, 1 centimeter, but I want to change the height to 10 centimeters. So that's going to be 0.1 meters. And here is my rectangular section. Please remember, when this gets assigned, its y-axis is going to be oriented with my default z-axis. So let's go to our line body. Now I can assign rectangular 1. And if the y-axis is aligned along the z-axis, this beam is going to be loaded along its weak axis. Let me show you here the cross section. I'm going to go to view, cross section, and look at this beam. If I leave it the way it is, it's going to be loaded along the weak axis. That's definitely not what we want to do. So we want to edit how the section is aligned. If you look at my line body, I have a yellow check mark because it is not yet aligned. So I'm going to come here and right click and choose select align unaligned line edges. We have a prismatic beam, so we only have to do this once because I have one line body. So when I do select and align line edges, I get the detailed view of line body edges too. And we're looking at the selection. And please be careful, because once you apply this, I do not know of a way to edit it. So you want to be careful. Okay. Now there are two ways we can use. I can choose to rotate my section 90 degrees or minus 90 degrees. So I can come here and give it a rotation. Like I can go like minus 90 degree. This will fix it. I can even do a 90 degree. I'll get the same effect. If I take it back to 0, this is where we started. My y-axis is aligned along my z. You see the y-axis of the section aligned along the z. The other way of doing it is to change the cross-section alignment from the default of plus z to a plus y. So I can come here and choose my y-axis and apply that. Once I hit apply, I'm done. So please be careful. Are you all with me on that step? Okay. So now I'm going to go to my line body. Right click. Choose, select unaligned line edges. I'm looking at the detail view, and I'm going to go to cross-section alignment. I do not have any alignment set yet, so it's simply going to the default plus Z. So I'm going to select that. And then I'm going to go to my graphics window and select my Y-axis. Good. And then I'm going to say apply. If I click apply, I'm done. So is everyone good? Okay. So let's apply it. And now we are happy with the section oriented to be loaded. When loaded in the transverse or perpendicular Y direction, it will be loaded, the beam will be loaded along its strong axis. So we're done with the geometry. I'm going to save my project. So come here and do save project. And I'm going to put it in our folder directory. And I'm going to call it simple beam example using beam elements. So that's the name of my project. It's updating the project in Workbench. And keep in mind, any parts in real life is 3D. When I'm using 1D elements, that's an idealization. So ANSYS still see a 1D element. But we are working in 3D, not in 2D. So we need to keep that in mind. So now we are ready to move to the model. If I come and double click on the model, that will start mechanical. Here comes mechanical. And here comes my beam. So we are working in 3D in X, Y, and Z. My beam is oriented along the X axis and loaded with a force applied in the Y direction. I'm looking here at the XY plane. So we get our geometry. We have our default material structure steel. If I check my line body, I will find that by default, it inherited the default material, which is structure steel. I have my cross section, the rectangular. We do not have yet a mesh. So the first step is to discretize, to break this continuous system into elements. So I'm going to go to the mesh and simply click generate. So ANSYS creates my mesh for me. Next, we want to define our boundary condition and apply our loads. Before we look at boundary conditions and supports, I would like to take a few minutes to discuss the degrees of freedom of beams and support types. So we are working on a beam that is one-dimensional, but we are working in 3D. We're working in the X, Y, and Z. We have a pin support, I'm sorry, a pin support at the left end and a roller support at the right end. And we are used to these symbols when we are working in plane. But what exactly is this pin support doing? Holding it into place, what does that mean? It's preventing the beam from translation, period. So that means that this support prevents translation in X, Y, and Z. Right? How about this roller support? Does it prevent rotation? You mean translation?
Yeah.
So it does not allow the beam to move up and down. And this is true when we are working in the XY plane. But if I'm working in 3D, it also should prevent it from translating in the Z. Or in other words, the way I see my roller, it is only allowing translation along the X-axis. Right? So this roller, so this here was a pin. Here I'm looking at a roller. And this roller, and instead of writing prevent, I'm going to write allows translation in the X direction. And as I mentioned that, I mentioned here prevents and I mentioned allows. But really, how many degrees of freedom do we have for a node of a beam element? I heard something good here. 6, right? So the degrees of freedom at a beam node we have 6, namely 3 translational degrees of freedom and 3 rotational degrees of freedom. Why do we have rotational degrees of freedom? Yeah, we know that this beam, when subject to this load, is going to bend like this. And what does this bending imply? When I had a face that was oriented vertically, like my marker, when the beam bends, this face can go like this. That's a rotation. But this face is represented by a point. So only a rotation would imply the rotation of the face. We do not have rotational degrees of freedom when we are using solids. Because when I'm using solids, every point represents a point in real life. Unlike this point on the beam element that represents a face. So please always keep that in mind. Having said that, let's also look carefully at this beam. When I'm working in 3D and I put a pin here, where I'm going to prevent translation in X, Y, and Z, but I'm allowing all the rotations. So this pin prevents the translation only, but it allows rotation about X, about Y, and about Z. Likewise, the roller would do the same. Okay. Now let's look at the beam as a whole. This beam being supported at 2 points cannot translate along X, because even though it is free to move here, it is held at the left support. Correct? And likewise, it cannot translate as a beam freely in the Y nor in the Z out of plane. How about rotation? If this beam wants to rotate about the Z axis, the roller would hold it. If it wants to rotate about the, so I said rotation about Z, right? If it wants to rotate about Y, the roller would also hold it. But how about if it wants to spin about itself? Is anything going to prevent it from doing that? What's going to prevent it? The pen, no. The pen only restrains translational degrees of freedom, but it does not hold it from rotating. So nothing is going to stop it from spinning. So if I attempt to run it with these supports being in a 3D problem like this in ANSYS, I'm going to run into problems because rigid body motion is going to be detected. So numerically, we have to let it know that this degree of freedom is restrained. So how do we do that? We want to do it without affecting the behavior of the beam. So I can introduce a support, like just to hold this from the outside by preventing this rotation about the x-axis. So I can add a restraint for the rotation about the x-axis at this end, and we need to do it so that numerically we get a solution. Okay, let's apply that in ANSYS Workbench. So first thing I want to do is I want to go back and look at my geometry. So I'm going to go to my display and turn off my thick shells and beams, and also my mesh. So I'm going to go to my static structure, and I can see my vertices and edges. I am going to go to the environment. I'm going to go to supports. And under supports, we have something called simply supported. So I'm going to choose simply supported. And I will select the left point and go apply. So now I applied a simple support that prevents translation in X, Y, and Z. Next, I want to do something that does what the roller is doing. Remember, the roller is allowing translation in the X, preventing it in the Y and the Z. I do not have something called a roller under supports, but I do have something called displacement. Since the roller is only affecting displacement, I'm gonna choose that displacement support and apply it to the right node. Please make sure you are selecting the vertex and not the edge. And I go apply. So now I have this displacement constraint that I still need to define. That's why it's highlighted in yellow. Now my 3 translational degrees of freedom are set to free. We want only the X to be free, but I want my Y to be 0 and my Z to be 0. So I have here the Y is 0, and I want to change the Z also to 0. Now this would mimic what the roller is doing to my simply supported beam.
It says rotation X, Y, and Z. Does that also?
There should be no rotation unless you pick something different. You pick displacement?
No, I think the one under support.
Okay, so you went here and picked what?
Remote displacement.
Yeah, that's not what we want to use. You got it? Remember now the beam can spin about its x-axis. Let's go and apply the loads. So under loads, I'm going to pick the simplest, which is a force. And now we have the point at the center that we want to select. And I'm going to say apply. And I'm going to define my force using components. So I change vector to components. And I only have one component along the y direction going downward. So it's a minus 1000 Newton. Let's try to run the beam like this. So if I come here and click solve, it's building a mathematical model. And see what we get. We get a solver pivot error. If I look at the details of my message, solver pivot warning have been encountered. This is usually a result of an ill-conditioned matrix due to unreasonable material properties. And we have here the second reason, an under-constrained model. So my model is under-constrained. And this is why I need to hold the beam from spinning. So the way I'm going to do that, I'm going to go back to my static structure or solve this problem. And I'm going to select a rotational, a fixed rotation support. This fixed rotation support allows me, like the displacement, to select which rotational degrees of freedom are restrained and which are free. And you want to be careful not to over-constrain it, because if you over-constrain it, you're going to solve a different type of problem. So I want you to pay attention to how I'm going to edit this type of support. So we're going to apply this fixed rotation to the outer end of the beam. Definitely, we do not want it to interfere with the behavior of the beam. So I apply it to the left node, and I want to make sure not to leave it fixed, fixed, fixed. We only want to fix rotation about X, but I want to change the rotation about Y to free, and as well as the rotation about Z to free. So now this spin is only restraining the beam from spinning about its axis. Now let's try to run the solution, solve, and see if this fixes our problem. And I'm going to prove that this fixed rotation is really doing nothing. It's building, solving the mathematical model. And this time we get a green check mark, meaning we do have a solution. First thing I want to show you is I'm going to put a probe to measure that moment reaction at this fixed rotation. And let me solve for that. So here is the moment applied. And look at this. I'm getting 5.6 times 10 to the minus 8 Newton meter. So what is that? Technically, 0, right? So this fixed rotation is not really doing anything. Is that clear? So let's look at the behavior of the beam. I always like to look first at the deformation. Let's see if the beam is doing what we expect. As the beam gets loaded, you see the bending. So this is what we expect from a simply supported beam. Next, we can start finding the support reactions. So I'm going to go to solution, use my probes to find the force reaction at the left support, which is simply supported. I also want to find the reaction at the right support, which is the displacement. Let's solve for these. We have 1,000 at the center, so I expect a 500 at each end. I look here at the right support, I have 500 Newton. In the Z direction, technically is 0, and in the X direction also is 0. We don't have any force. The second force reaction, likewise, we get the 500 Newton that we expected. Next, we want to put a probe to find the displacement at the center. So the formation, and I want to put a probe at where the load is applied, apply. And we want to find the y-axis deformation, because we're not really expecting to go anywhere. So if I solve here, I'm gonna, by the way, I can come here to the formation probe and rename based on definition. So that change the name to y-axis deformation. And let's look at the results. I get a minus 0.125 meters. That's a significant deformation, right? If I duplicate this without results and change the result selection to all, that will show me, or total rather. I solve it, and I find here that the total is the same as what I get in the y direction. That tells me that the only component is displacement in the y, which is what we expect. Next, we can look at beam results, and I can look at the bending moment. I can look at the shear force. Now, do we expect any axial forces? No, but let's do it. Do I expect any torsional moment? No, let's do it. So let's solve for these. Okay, here is the total bending moment. As we expect, I get 0 at the supports, and I get my maximum at the center. And I have a maximum bending moment of 2,500 Newton meter. Shear force is uniform through the beam, 500. Of course, it's the first half is positive 500, the second half is negative, but I'm looking at the magnitude. Axial force is 0, torsional moment is practically 0 as well. Right. Now, as you know, for beams, if I go to results and look for stresses, they're all grayed out. Because I strictly have beam elements. In order for me to see stresses, I need to use the toolbox and use the beam tool. This would allow me to look at direct stress as well as combined stress. Let's solve for that. Direct stress, as we expect, is all going to be zero. The bending stress would be the same as the combined. So if I come here and look at the combined, I'm getting this 150 megapascal. That's the maximum stress. If you want to verify, I can go to beam tool and go insert beam tool, stress, and put the maximum bending. That should be the same if I solve it. I look at the maximum bending, I get the same number as the maximum combined. And that proves the point. The very last thing we want to do is to look at shear and moment diagrams. In order for me to look at shear and moment diagram, I need to create a path. So I'm going to go to the model, right click, insert, choose construction geometry, and then pick path. It shows the detailed view of a path, and I want to make sure to change the path type from 2 points to edge. Otherwise, you won't be able to select it when you're defining shear and moment diagram. Now I need to define my path. So I select my first edge, control button, and select my second edge, and say apply. That creates a path from the left end of the beam to the right end of the beam. Now I'm going to go back to my solution, and I'm going to go to beam results diagram, select shear and moment diagrams, and I need to select the path I created. See the path? And here, the type of the diagram I'm creating is total shear and moment diagram. So I can come here and solve, and I get a total shear, total bending, and total displacement. So all the results are going to be positive because I'm looking at a magnitude. If you want to see it like you would sketch it, I'm going to copy, come here, and duplicate this without results. And instead of selecting the total, you really want to select directional shear and moment. And it should be the VY MZ UY. But there is a bug in ANSYS, and sometimes it would flip them. So just make sure you verify your answers. So if I select this and solve for it, you see here clearly it is showing all zeros because of the fact that they are flipped. So if I come here and rename based on definition, this is Y shear force, and the Y shear force should not be zero. I'm going to show you that it's showing it in the wrong location, duplicate without results, and now I'm going to pick VZ. And we know our forces are going in the Y directions, right? So let's solve. And now I see what I expected. So this really should be the shear force in the Y direction. And again, because of this bug, it's flipping it. Here is the bending moment, also shown as negative. And here is the displacement. So only one that is displayed correctly is the displacement. The others are showing a flipped sign. So just bear this in mind, but it is showing the results that we expect. Any questions? Okay, couple of pointers, because I want you, on Tuesday, we do not have a class meeting, but I would, because of the career fair, but I would like you to work on homework number 6 until we meet again a week from today. Homework number 6 about shaft problems. When the first problem has a prismatic shaft. So you're simply going to create points anywhere we have a support or a load applied. A bearing support may be modeled as a pin support like we did here, because it's preventing the shaft from translation, but it's allowing it to rotate to some extent. So it's not perfect pin, it's not perfect fixed, but it's somehow somewhere in between. So we're going to use a pin support to be conservative. You want to make sure to prevent the shaft from spinning, even though we know it's rotating, but we're doing a static problem. If you want to attempt the second problem, you want to make sure to use add frozen and use different types of section for 3 regions. Even though the bearing is not applied to a point, we want to apply the pin support to a point, because the length where the bearing is applied is relatively small compared to the length of the shaft. So it is an acceptable approximation to apply the pin support to a pin. All right. Good luck to you going to the career fair, and I'll see you all a week from today. Thank you.